In this episode, we will be learning what the Laplace transform is. The Laplace transform is actually very useful in computing ODEs. So before we show how useful it is, we first need to learn how to use it properly. The Laplace transform is a function of functions. Let that soak in. A function of functions. Well, normally a function has input and it has output. But in this case, our input is going to be a function, a continuous function with certain properties. For now, don't worry about what kind of functions we plug in, but you're going to plug in a function and then you're going to output a function. So the Laplace transform of f is simply this integral. Whatever you plug into the input is going to go right here in the integral. But the integral gives you a number, and we want a function. Well, the only thing that varies in here is going to be the s right here. So the Laplace of f is going to be a function of s. So since we're inputting lowercase f, what we're going to be getting is capital F. So this is simply a notation to help us keep things in track. So if we're calculating the Laplace of lowercase f, we're going to be getting capital F. So if I want to figure out the value of capital F at, say for example, the number 5, what I do is I plug in that 5 here in the exponent, and right here, and it's going to give you a different number. So you do, in reality, get a function. So in computing the Laplace of a function sometimes can be complicated, but using some of its properties, such as linearity, then it makes things easier. For example, let's say for a moment you know the Laplace of t, which is this, which is a good exercise to figure that out on your own. And let's say you know the Laplace transform of t squared, which is this here on the left. Well, if you want to calculate this linear combination, all it really is 2 times the Laplace of t, which is 1 over s squared, plus 3 times the Laplace of t squared, which is 2 over s to the 3. So using a table is helpful. Recognizing Laplace maps that you've already figured out what the Laplace transform is, recognizing those in linear combinations is going to be helpful and will save you a lot of time. So if you want to do it, start from the beginning, all you have to do is just go straight to the definition. So for example, let's take a look at this map here. This is the Heaviside function. The Heaviside function is 0 everywhere on the left of 0, and it jumps up to 1 after 0. So let's go ahead and calculate the Laplace transform of the Heaviside function with the shift t minus a. So let's look at here at our graph. So let's say a is somewhere over here. All we're really doing here is just shifting the graph over. So it's equal to 0 on the left side of a, but at a and afterwards it's equal to 1. So let's go ahead and calculate the Laplace transform of this. So by definition, it is good to do things by definition so that you understand what is going on. So we have e to the negative st times u of t minus a dt. So since we said that u is equal to 0 on the left side of a, then everything vanishes. And afterwards, the u of t minus a becomes 1. So we have e to the negative st dt. All right. Well, this is something we can compute. What we get is e to the negative st divided by negative s evaluated at a and infinity. You can go ahead and calculate the limit on when you take the limit as t goes off to infinity, and what you're going to get is 0. And when you plug in a, you're going to get minus e to the negative st over negative s, so you get e to the negative st over s. All right, so I gave you guys two ways to compute the Laplace transform of functions. One way is the definition, which is this example. The other one was using what you know, using tables of Laplace transforms, and using the linearity property.